What?
And we look edges that go to other temporary places. So 4 plus 4 and 4 plus 6. The 4 plus 6, that beats infinity, so the infinity becomes a 10 and points back. The 4 plus 4 is 8, but that's worse than 6. And the algorithm continues in similar fashion. Okay, so what do? We find the cheapest vertex. That would be the cheapest temporary vertex is 6. We make that permanent. We look at the edges that go out to other temporary vertices. 6 plus 5 is 11. No thank you, says the 10. 6 plus 7 is 13. That beats infinity, so that becomes a 13. 6 plus 1 is 7, so that's better than the 8. So we change that 8 to a 7 and point back to the 6. All right, next, the next cheapest one is a 7. We see that 7 plus 5 is 12. That beats 13. Now notice that even though we reached vertex B, even though that was our goal, we can't stop the algorithm now because that 12 isn't permanent yet. There's no possibility that it's going to change. Okay, we go to 10, that's the next cheapest temporary edge, and we look at its vertex. We look at that 1. 10 plus 1 is 11. That's less than 12, so that 12 becomes an 11. And finally, we go to the 11, we make it permanent, and the algorithm stops. By the way, did you find the shortest path that has a whole lot of 11? What is the shortest path? Right now, we have found the shortest path, not just from A to B, but we have an entire tree of shortest paths from node A to all other nodes in the graph. If you just want to find the shortest path from A to B, you just start at B, and you backtrack to the vertex that gave you the last block. So here we have 11 points to 10, and 10 points to the 4, and 4 points to the 3, 3 points to the 0. There's your shortest path from node A to node B. So, you may ask, how fast is Dijkstra's algorithm? So, suppose G has n vertices and n edges. Okay, let's analyze this algorithm. Step 0 has time n. And step 0 is the one where you assign 0 to node A and infinity to everything else. You got to do one thing to each of the n vertices, so it has time n. Step 1 of finding the cheapest temporarily labeled vertex, that's called at most n times. And when you're looking on your list of all the cheapest vertices, that takes you at most n steps. So step 1 is total amount of time that it's going to be used. It's going to be at most n times n, at most n squared. I mean, very clear. Step 2, when we're basically looking at each edge once the vertex becomes permanent. So each edge is going to be examined essentially twice. Only one of those times are you really going to use it. You'll examine it at most twice. So this has a time of at most 2 times n. So I've got n edges. Each edge gets used at most twice. Roughly speaking, if our graph has n nodes and n edges, then Dijkstra's algorithm takes no worse than about n squared plus 2n squared. And since n is less than n squared, this is no worse than 3n squared steps. Computer scientists say this algorithm is on the order of n squared. They say big O of n squared. What that means is it's on the order of the most n squared steps times a constant. And you can find it on the constant. It takes you like 10 n squared.